This video is going to start the lecture series on how to use KiCad to do PCB development. In this first video, we're just going to start with doing a footprint, and we're going to start to piece together a schematic in a way you've probably already pieced together a schematic for schematic review. But now we're going to talk about how to pay a little more attention to the schematic components you use, making sure you're not using just like spice models, making sure you're actually using components, how to connect footprints, how to create wonky footprints, kind of an easy way to do that. So, I'm going to try to make these videos little pieces, sort of 1 hour at a time. So this one will be about an hour. I'll try to move fairly quickly. I know most people, when they use these, they pause, they move forward, they move backwards. So knowing that, we're just going to kind of try to work quickly, use the pause button if you have to, use the rewind button if you have to. But we're just going to go piece by piece from scratch, how to do a basic PCB development. So behind here is what I'm going to do as an example is I'm going to do a breakout board. It's going to be a breakout board for a LoRa radio module. The LoRa radio module is one that I'm using. I've already created this breakout board, so I'm going to kind of do it again just to show you. It had some things that came up in the development that are useful for what you might be doing with your project. So this is an example. This is a similar breakout board that was done by SparkFun. So a couple things to note. They have this power enable pin, and the power enable pin, they sort of have a totem pole they have an NMOS transistor on the bottom and a PMOS on the top. This is the proper way to do if you have a voltage that might potentially be a lower voltage turning on and off a higher voltage. This is the way to do it. So if you're trying to have a signal that's a lower voltage than the voltage you're turning on and off, this is the way to do it. You have to use a pull-up resistor to get the high voltage on the gate. And you have to use, an NMOS to pull that down. So you kind of have to use a pull-up resistor if you have a low voltage switching on and off a high voltage. But this is a good way to do it. And I'm going to do it for this one. This radio consumes about an amp at maximum current. So that's, consuming that much current, it's nice to be able to fully cut power to it. It's nice sometimes to be able to control it by fully cutting the power to do resets when resets might not work. Or just for saving power, for power saving. So some of you might have peripheral boards that have a bunch of different stuff on them. A good way to make sure they're going into real low power mode is to just totally cut power. So we're going to kind of copy this looking at this. But we're going to start with a footprint that I'm using, which is here. So this is the actual module that I'm using. This is the data sheet for it. The module is the E220. I think it's the E220. Yeah, E220. So this is the footprint for the module. It has castellated pins on the side. So castellated pins, it's basically it's an edge pin. It's a pin on the edge of the board, but it's designed to where a pin could be soldered in. So there's a little hole. So these are plated all the way down the side. A lot of you have boards that have these. And we're going to make a surface mount footprint for this. So this would allow us to take this board and solder it onto the surface of a PCB. So to do that, we're going to kind of be building pads that extend out beyond the edges of these pins. But we're going to use, you see the dimensions here are a little wonky, right? They're 24 millimeters across, 38.5 down. But more importantly, the pins are a little weird, right? This first pin is 2.61 millimeters from the edge. And then they're 2.54 inch spacing, which is fairly standard. And then they're 7.60 spaced here. That almost feels wrong. Like it feels like it should be 7.62 spaced. 7.62 space would be 0.3 inches. Maybe that's an error in the data sheet. I don't know. But if the data sheet says 7.6, I'd probably go with 7.6. And so it could be somebody did a rounding error, but this is a weird footprint. This is not a footprint that's going to fit cleanly on any sort of grid. So I like it as an example for showing you how to do wonky footprints. If you're looking at a data sheet and you're like, look at these dimensions, look at the references they're using, how am I going to build this? We're going to go over that today. So we're going to go into KiCad, and I have a blank project created. So if I open this blank project, you can see it's just nothing here. And so we're going to start by creating this part, this library part for this. So I'm going to minimize this a little bit. I want to always kind of be able to see what I'm looking at here. So I kind of want to always have my data sheet in view while I'm working with this. And sometimes you got to kind of, it's good, it's nice to have two monitors. I do have two monitors, but for the purposes of this, I kind of want to screen record on just one monitor. So the first thing I'm going to do is I'm going to create a new library. So I'm going to go to the symbol editor, and I'm going to do new library, and I'm going to create a library just for this project, and I'm going to call it, you can see I already have the one that I did here, but this is LoRa demo. So I created this LoRa demo library for this particular project, and then I'm going to right click and I'm going to go new symbol. And the new symbol name, this is the LoRa E220. So it's the eByte LoRa E220. I'll just call it that. U is okay. This is an integrated circuit, so U is an okay symbol for that. And we'll click OK. Now it throws those things on here, and it doesn't really matter where you put them here. So the first thing we're going to do, we're just going to do the schematic symbol first for this thing. So going back, we have, one thing that's weird about this is we have lots of pins that are ground here. We have lots of pins that are connected to ground. And you don't normally want to show all these ground pins. And so I'm going to show you how to do it where you don't have to actually show all the ground pins. But we're going to start. So what are our signals? We have ground, we have VCC, we have RX, TX, DIO, DI1, DI2. We've talked before about creating these symbols, and I'm just going to kind of quickly throw this down here because I'm not too worried about this. I more want to get to the footprint. So I'm just going to add pin. I will show you how to do multiple ones of the same one. So this pin name is going to be ground, and the pin number is going to be 1. And it's going to be visible, and right is fine. So we'll put this, doesn't really matter where we put it now. We'll put it ground. We do want to check our grid. So we want to make sure that our grid is set to a reasonable level here. So the grid is 1.27. I actually want the grid to be 2.54. And if after doing that, this thing is moved, we got to readjust it to get it back on grid. Okay, so grid's 2.54, the thing's there. Now, we have lots of other ground symbols that are other pins other than pin 1. And there's lots of ways to deal with this, but one of my favorite ways to deal with this is basically just to place another pin. Oops. And we'll call this one ground. And the pin number will be 2, but we'll make this not visible. Oh, you know what? I also should have, the electrical type for ground should be power input. Okay, we'll go back and edit that. So I want to change that for this one too. So this one's going to be electrical type power input. And I'm going to make this second ground pin not visible. So I'm going to call it ground, make it not visible, power input, okay. And now I'm going to copy this and I'm going to paste it. Now you can see when it's not visible, it turns kind of pink like this. So my other ground pins here, so this is pin 2, we want pin 3. It looks like pin 4 is also ground. Pin 5 is ground. Pin 11 is ground. And pin 12, and then we need 2 more. We need pins 20 and 22. 20 and 22, okay. So this one will be pin 12. And then pin 20. And pin 22. Okay, so I've created my one visible pin 1 ground pin, but then we have all these other ground pins that are connected to ground that are not visible. And what I'm going to do is I'm going to take these, and I'm actually going to take each one, oops, and move it to overlap this thing. So I created all my ground pins. The ground pins are associated with the physical pin on the chip. This is going to tell the software that, hey, this pin does need to be connected to ground, or it is there. But I also overlapped them. So when we make the electrical connection, it should connect automatically. I'm not, we'll see in the future. This could be a mistake. I did this a while back, and I feel like there was something that screwed up with this. But, well, we'll go with what we got for right now. It's not the symbol that I'm too worried about here now anyway. Okay, we got a couple more pins to do. So I'm just going to go in pin order. So RX enable, TX enable. These are 2 pins on this radio that the radio has a power amplifier. So basically you need to determine, are you amplifying the signal coming in or amplifying the signal coming out? So you have to specify the directionality for the power amplifier. So that's what these are just digital signals that are specifying that. So we're going to place another pin, and this pin should be visible. This pin name will be RX enable. This is pin number 6. This is a input, and okay, put that there. And we're going to place another one. And this one is TX enable, pin number 7. Now, what I like about KiCad is, the last one that I created was visible, so it kind of keeps the settings, the directionality and the visibility of the last one you created. It keeps that, which I like. So, and then we'll do pin 8, which is, this is DIO2. These are general purpose IOs that are used by this. This is pin number 8. Oops, DIO1, no, this is DIO2. Pin number 8, this is bidirectional. Okay. Now 9 and 10 are VCC. So I'm tempted to do 9 and 10 over here. This will be pin number 9. And this is power input. Oops. We'll do that like that, and then what I'm going to do is same thing, VCC pin number 10, but this one I'm going to make it not visible. It's power input, and have it overlap. Okay. 11 and 12 are grounds. We already took care of those. Looks like we're good. So now we go DIO1 is pin 13 here, so I'll place another one. And now we have to, the last one we had was, all sorts of different stuff. So DIO1 is also an input-output. DIO1, pin number is 13. And be really careful when you're doing this because it's very easy to do this stuff wrong. You make a mistake here, you make a pin number mistake, you make a name mistake, you flip 2 things, you might not notice it until you're struggling and you can't get the thing to work. So really, I'm moving a little fast, I've done this already, but pay attention, be very careful when you're doing this. Get somebody else to look at it. Say, hey, this chip's really critical. Can you just look over the data sheet, look over my footprint, triple check that it's correct? It's sometimes better to wait until you're in the PCB, when you're actually building the PCB to check this stuff. Because when you're actually checking the PCB, you should have a pin name so you can kind of look at what you labeled that pin, what you labeled that signal. You can look through the data sheet for the part, look at what's actually on the PCB, and just triple check that it's right, because there's no, you're totally in control here. Any mistake you make is not going to get caught. So a lot of students, almost all students, make little mistakes. They use the wrong pin number, something like that. It can be really tough to find them. Everybody assumes everything's going to work until it doesn't. And so, part of developing an understanding of PCB design is learning not to trust yourself, learning to say, I didn't see anything wrong, but that doesn't mean there's nothing wrong. So assume you messed up, assume you screwed up, assume you need to find where you screwed up and make those changes before making those changes requires you to do a whole nother PCB design. Okay, so DIO2, DIO1, we got a busy pin, that's an output. So let's do, that's pin number 14. That is an output. And reset. SRT. So and when you have a pin labeled like N reset, Normally that means it's not reset, so that's showing kind of a bar over it. So there's other ways to show that, but starting with an N is a fine way to do it. But just when you see an N, when you see like here we have NSS, that means not slave select. So it means it's the slave select pin, but the not means it's active low. So it means that you have to pull that pin down to a 0 to actually select the slave device. So N reset 15. When I talk and do this at the same time, I screw up all the time too. So you'll probably see me screw up something and then you'll laugh at me, which is fair. I've kind of gone down far enough over here. I'm gonna switch to the other side of the board now. So I'm gonna place a pin here. Switching to the other side of the board means I want to flip the orientation. I mean, I can always rotate it to flip the orientation too, but I'll just do it like this. So this is MISO, and that's an output, and the pin number is 16. Try to line that up. And this one is MOSI, pin number 17. That is an input. And specifying the output input, a lot of students are tempted to just do, everything is unspecified or bidirectional or something. Specifying it helps the software catch errors. So if you specify it and you specified it correctly, it can help the software say, hey, you got two outputs connected to each other, what's going on? And at least it'll cause you to go, wait, did I mean to do that or not? It'll kind of stop you a little bit. So MISO, MOSI, SCK. And so again, this is that slave select pin listed as NSS because it's active low. We already got the grounds taken care of. There's one more thing, which is this antenna, which is pin 21. Now, sometimes with antennas, in this case, because our pins are a little weird, sometimes with the antenna, you kind of want to have it separate from other stuff, just so it's a little more visible. So what I might do is I might just take these pins, move them like that, and then move the antenna down here. Okay. That looks good. This is probably where I go through and like double check all the numberings and stuff, but for the sake of brevity, I'm going to skip it. Why are both these power inputs? Make sure. Okay. So sometimes if it's covering everything up, you can maybe you can't. Interesting. Oh well. Thought there was a way to order them. Oops. And now I screwed it up. Oops, this thing's rotated. That's weird. Okay. Glad we caught that. Okay, now let's put a body on this thing. So we're going to place rectangle. Escape. We're going to do fill body with background color. That looks good. Now we can move these, although the software is gonna, no matter where you put these in KiCad, the software is gonna move them to, to the default location for the schematic that you're using as specified in the schematic. I'm gonna select everything, and I'm gonna move just pin 1 to the center here. So I'm gonna move pin 1 to the center of this array, and it looks fine. Okay, we're gonna save that, and then we're gonna close, and we're gonna go to. Well, we'll go back to our schematic, and we will go, let's go to the footprint manager. So we'll create the footprint for this now, which is kind of what I was trying to get to. I don't know why I started with the schematic, but with the symbol. It takes a long time to load when I'm running OBS, when I'm recording. This computer's not this bad, but it's just when I'm running OBS, it just kind of chokes a little bit. Okay, so once again, I want to create a new library for this thing. It looks like I don't see my thing here, so I'm going to create a new library. It'll be just for this project. It'll be Laura demo. And then we're going to do new footprint. Enter footprint name. So this is going to be eByte E220 radio. Okay. Now there's a couple things to note here. What you see here this is reference, so that's going to be the designator. So whatever this gets annotated to, U7, U5, U12, that's going to show up. So that reference is going to show up on the actual top layer. So if you look at this is the front silk screen. It's going to show up on the front silk screen. Why is it repeated here? So it's repeated here with this reference here. These little grayed out areas are what show up in the software but won't show up on the PCB. So the nice thing about having this reference shown here and here is even if you decide I don't want this annotation listed on the circuit board, if you just say I don't want it to show up, you know, I'm tight for space, I don't want to have a bunch of letters and stuff all over the circuit board. You should, if you have the space, you should do that. But if you say I just don't have the space for it, you can get rid of the actual silk screen but still see which part this is when you're actually using the software. So that's why it's kind of nice to have it repeated like that. So just like before, I'm not too worried about this stuff here. What I want to do is I want to look at, I'm getting messages from, some of you might be trying to get a hold of me, so let me just get on my email here in case. Okay. So if one of you needs to get a hold of me, I'll get it there. So looking at this, so you know, this is a very strange layout, which is why I like this. It kind of looks like it's shown upside down here, but we're just going to do it. One of the biggest mistakes students make when doing a footprint is they do it backwards. So we're going to do, this appears to be the top view, so this shows the little shield. It should be labeled top view, back view. It's not, which is a problem. If it's not, go to the actual physical part. See which one's the front view, see which one's the back view. You don't want to get the footprint backwards. That's a fatal mistake. There's no way to fix it. So this looks like, you know, pin 1 is shown here. Pin 1 is usually the top left corner, so it looks like this is kind of rotated. It's fine. I'm going to keep this as is. I'm going to keep this in its orientation like this just to avoid making mistakes. So I'm going to build this part in this orientation. If we want to rotate it later, we can rotate it later. I'm just going to copy exactly what's shown here. And I'm going to copy it from the top view here. So the first thing is these pads. These pads are 0.5 millimeter. There's the top pad and bottom pad. So the bottom pads extend a little further. So the bottom pads extend a little more copper into the board. If the bottom pad is 1.25 millimeters, is 1.5 millimeters high, and it hits the cancellation halfway, I'm going to make pads that are centered on the edge of the board that are actually 2.5 millimeters wide. So I'm going to go with a wider one. So to start, I'm going to go, well, before I get to the pad, let me just do the outline. I like to start with the outline for the part. A lot of people draw it later. A lot of people start with the pads. If I start with the outline for the part and I know it's correct, it's really nice because it lets me kind of have a sanity check as I'm doing this, that things are kind of in the right place. It'll make it so that it looks like what I'm expecting. It's not the only way to check it, but it's a way to sanity check. So this thing's 24 by 38.5 millimeters. So the first thing I'm going to do is, while in the front silk screen, I'm going to draw a line. And I'm going to start here at the I'm going to make sure my grid is correct. So my grid, so right now, yeah, so my grid, if I'm trying to build a 24 by 38.5 millimeter box, I probably want a 0.5 millimeter spaced grid. So we're going to start there, and I'm going to click right here at what's the current origin. I'm going to click on that, and then I'm going to go over, and it shows me until I hit 24 millimeters. So 24 millimeters. Then I'm going to go down until I hit 38.5. I'm going to go over, should be 24 millimeters. I'm going to go back to where I started. Okay, and I'm going to hit escape. Okay, so now I've drawn the outline for this part. Okay, so the first thing I want to do is, we have a bit of an issue here in that these start at 2.61 millimeters from the edge. That's a really weird distance. So for this first pad, alignment's going to be a little difficult. So basically this first pad, top left corner, pin 12, should be based on this 2.61 millimeters down from this top edge of the board. So currently this is my origin, is right here. So what I'm going to do is I'm going to just start by placing a pad. So I'm going to place a pad, and I don't really care where I'm going to put it right now. I'm just going to click it somewhere and hit escape. Then I'm going to go to this pad, and I'm going to change the dimension. So it looks like, because I already did this. So this one, the X, okay, so the X size for this, I want to double this. So I want to do 1.25 times 2. So I want this to be 2.5 as the X size. And the Y size, I want it to be 1.5. Okay. Now, so right now this pin is centered on the edge of the board, which is about where I want it, but I need it to be 2.61 millimeters from the top. So I'm going to click into this again, double click it, and I'm going to say, okay, this position is 0, but the Y position, instead of 3.5, this needs to be 2.61. Okay. So now, by manually changing that coordinate, I've now guaranteed this pad is centered on the edge of the board and that it's 2.61 millimeters down from the reference, which was here. Now, once we have this first pad down, and this first pad is not pin 1, this first pad is pin 12. So now what I want to do is I want to basically keep dropping pins 12, 13, 14, 15, 16, but the pitch of these has to be 2.54 millimeters. 2.54 millimeters is 1/10 of an inch. So there's a couple things I want to do. The first thing I want to do is I want to set my grid to 2.54 millimeters, 0.1 inches. But I also want to now make the center of this pad my new reference point. So to do that, I'm going to go edit, okay, place the footprint anchor. So when I place the footprint anchor, I want to make sure it snaps to the center of that pad. Okay, so now this pad, this is now my new 0. So basically everything that I do is now relative to this pad. So if I copy this and paste it, I'm now pasting copies of this with exactly the right pitch. And so let me just start by it's a little tedious to do this manually. You don't have to do this manually. So let's try this. Let's try place, add pad. And now it's going to default to 17. So it's going to place a copy of the pad. This is almost a better way to do it. It's going to place a copy of the pad, but it's going to just start counting pins. So 17, 18, 19. Okay, now the problem is to get down to 20. Well, it's this weird 7.60 spacing. Before I do that, I'm going to go over to the other side because these pins should be automatically spaced correct now. So the other side starts at 4 down here. So I can't, you see, because my grid space doesn't allow me to hit it right on the edge. So I don't really care. I'm just going to place it so it's lined up vertically. I'm going to place that. And I'm going to go into this pad. And I'm going to specify that the X position now, it's a 24 millimeter wide board. So this X position needs to be 24. To be centered on the other edge of the board. The Z should have been correct from what we had, and now this is going to be pad number 4. Everything else still looks the same. Okay, so now that's pad number 4. Now here's what. Now this edge of the board is a little weird, so I'm going to create a new reference. So I'm going to do, once again, I'm going to do place footprint anchor. I'm going to center that on this pad. Okay, so now this is my new reference. So now if I do place add pad, it should start with 5, and it should now be referenced to that previous one. So 5, 6, 7, 8, 9, 10, 11. See how slick that is? So when you change the pad reference, now every pad you do is going to be relative to that. It makes it really easy to do these kinds of things. Now we have to drop down to these other pins that are further down the board. So these next pins are, technically they say they're 7.60. 7.6 millimeters is weird. It should, my guess is it should actually be 7.62 millimeters, but it is what the datasheet said. If I had this physical chip, I would probably try to measure it with calipers, but even measuring it with calipers, your chances of getting 0.02 of a millimeter precision, I don't know. It's going to be close enough either way. 2.6, 2.62, it might be a little bit off. The data sheet says, the data sheet says 7.6, not 7.62, so we'll go with that. So I'll just start, because I'm already on this side over here, I'll just start. My reference is now pin 4 over here. My reference is currently pin 4. So I'm just going to place this wherever, on this, lined up on this edge, and this should be pin 3, I guess. This will be pin 3. It's got to be 7.6 inches, so it's got to be 7.6 inches from this bottom pin here, which is already our reference, so we're good to go. So let's take this, and let's do, well, we might as well just call it pad number 3 because we're here. But the Y now, the Y, oh, that's interesting. Oh, not the size. Sorry, the Y here, 7.62 is what it wants, which my guess is what's actually correct. But it should actually be 7.60, according to the data sheet, which I assume is wrong. Okay, now because we barely just shifted this thing, but we want to set a new reference now. So we want to set a new reference on this. See where the little crosshair is in the middle of pad 3. So we're going to do edit. View, place, footprint anchor. See, now this is weird, right? It's so close, right? The grid and the footprint are so close to each other. But we want the footprint part. Okay, so now we're centered on 3. And so now we're going to place add pad. It's going to number it wonky. I don't really care. We're just going to go back and manually change these. So this one should be 2. This one should be 1. Okay, now same thing. Now we're going to do the same thing on the other side. So we're going to go, now we have to go over 24 in the other direction. So we'll do place add pad. So that's not lined up correctly, but we can click on this pad. And we should be at negative 24. And this pad number was 22. And now we're going to, once again, place the footprint anchor on that pad. I'll just copy paste it. Boom. Boom. Okay. So all we have to do is change these numbers. This one should be 20. No, that one's 22. That's correct. This one should be 21 now. And this one should be 20. Okay. So now that should be good. I would zoom in. I would check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You know, I would double check the dimensions. I would kind of make sure everything looks right. Make sure everything looks correct. What I'm going to do now also is I'm going to draw, there's this little RF shield and this little IPX connector. I'm going to kind of just draw those with silkscreen just to make it a little more clear where the parts of this radio are. So I'm going to set my grid a little bit finer. I'm going to set my grid to 0.25 millimeters. And I'm not trying to be too precise with this. I'm just trying to kind of copy what the data sheet does here. Looks like it goes down pretty much to here. Not being precise. I just hope this lines up. Ah, it doesn't quite. There we go. Okay. Not great, but it's fine. If we want to kind of balance that a little bit, we could move it like that, and then there we go. Okay, that's a little more precise. And we can do the little IPX. So the IPX connector is normally actually a circle. So we're going to place draw a circle right about here-ish. Whatever. Close enough. The person's going to know. Now, for this, you know, when it's a radio like this, a lot of times you don't want to route high-speed traces under it, so we can add a note if we want to. We can even add the text. We can add the text in silkscreen. It doesn't really matter. It's going to be covered by the radio. So we could do not route. Okay. Give ourselves a little note, right? I don't know. It's a little tacky. This just probably shouldn't be done in top silkscreen, but I'm going to do it in top silkscreen just for fun. I kind of like, again, when you're placing like a physical radio, sometimes I'll put the reference inside. You know which part it is. So this is just for assembly, right? So I'm going to put the reference inside just for fun. I'll move this here. Move this here. Okay. So that to me is good. This is the point where normally I'd triple check it, but we will save that. Okay, so that's the footprint. That footprint is now complete. We can now close that. Now there's a couple options that we could do. One thing we can do in KiCad is if we go back to our symbol editor and we open up, so I think it was LoRa demo. So we can set a default footprint for this. So that footprint we just created, we can set a default. So we can find our LoRa demo right here, and we can specify that as the default footprint. So, and we can also link to a data sheet, things like that if we want to. Yeah. Okay, so now it added an extra little thing, which is our default footprint, which fine. Okay, but now we have a default footprint attached, and we can save that too. Let's go back to our schematic. So we're going to place this part in our schematic. Scroll down to our demo library. Okay. And again, I like to make sure when I first plop a thing that it's aligned on the grid. You might not be able to see it, but it looks like it is aligned on the grid. I'm going to hit escape to avoid that. Okay, now let's just double click this and make sure that, yeah, so it did use that default footprint. So if we hadn't done that, if we hadn't connected the footprint to the part, we could have still specified this later. We would have had to specify it later, but for now, you know, it's done for us. We know this is the only footprint anybody's ever going to use for this part. So we might as well link it and it'll be okay. And there's a couple more things I want to do, and then I'll call it good for this lecture just so we don't go too far. So the power control pins. Now this gets into some issues that are going to be important to know. If we go back to our SparkFun thing, well, they have these transistors here. So they have a PMOS transistor here, an NMOS transistor here. These are capable of carrying a fair amount of current, and you know it looks like they're having when you when you enable power, it allows both VCC and the 3.3 volts in. So there's two power signals coming in. VCC, which is a high voltage, which is a 5 volt to drive the radio amplifier. And then there's 3.3 volt, which is just drives the circuitry, the electronics and stuff. And so it cuts them both. It's really important to cut both. If you're ever cutting power to something, you want to fully cut any power signal. You don't want to have one power disabled, the other power enabled. So the same signal cuts both of these, which is probably the proper way to do it. But there's something to know about surface mount transistors. There's no real standard for surface mount transistors. So where the source, drain, and gate are depends on the particular footprint, depends on the particular part. One thing a lot of students do is they say, oh, I found a symbol, it was the default symbol. I found an NMOS transistor and I used it and it doesn't work right. I gotta flip it upside down, or the drain and the gate or the source are weird. I'm gonna show you how to make sure you get that correct. So what we're gonna do is we're gonna say, I don't know what these transistors are. We're gonna build this same circuit, but we're gonna use transistors that we know we have out of the parts library. So if I open up the SMD components library, and I look here at the transistors that we have. So our power transistors, which are 1.9 amps and 1.4 amps, which really cut those currents in half. If you want to know the actual current, you'll probably be able to pass through them, which is fine. That should be okay. So our N channel is this thing right here, and our P channel is this thing right here. So when we build these, we want to be very careful to choose the right footprint for these. And the order of like source, drain, gate is going to matter depending on the part. So if we look up this particular part, so let's take this and copy it. And then we'll go back to, we'll go to another SparkFun window. So if we go, well, yeah, so let's go to this. I always don't click the add thing. So this is the part we're looking for. This is the part we have in the parts library. And it looks right, N channel 20 volt, 1.9 amps. Let's look at the data sheet for that. So if you look at the data sheet, it does gate, source, so on a SOT23, this pin right here is usually pin 1. It's actually kind of not good that they don't show the pin numbers on this. But for if you look up an SOT23 case, you'll see that this pin is pin 1, this is pin 2, this is pin 3. So what we have here is, this would be what's called a GSD PMOS transistor. So that means pin 1, 2, 3 in order is GSD. And we got that from the data sheet. So let's go back to so remember GSD, let's go back to KiCad. And let's place these, was this the NMOS? N channel, yeah. So N channel GSD. So let's place, add symbol. So I'm just going to search for NMOS. I didn't mean to do that. What is it? Is it A? Yeah, A. It's better to learn hotkeys. So just don't hit. So skip this PSpice. A lot of students, when you're doing your schematics, you went to the PSpice thing. That's fine if all you're doing is assembling a model for simulation. If you're assembling actual parts, you want to go to the actual part. So here's what we have. We have Q meaning the symbol for transistor, Q NMOS. So you have DGS, DSG, GDS, GDSD, GSD. So all of these relate to what I was saying here. All of these relate to, you know, what is the order? And getting back to this, right? We were GSD. So we want to go Q NMOS GSD. So 1, 2, 3. The 2 was on this side of the body diode. The 2 is on this side of the body diode. Okay, that looks correct. Now that's a step that is not intuitive, and a lot of students don't know it, and it screws up their whole thing. There's so many students that have to like take a transistor and flip it upside down and bend the legs and do all kinds of weird stuff because they don't pay attention to this step. You don't know to pay attention to this step. That's why I'm covering it in this video. So Q NMOS GSD, and we're going to place that just kind of like what they did in the SparkFun one. We'll just place it here. And now what I'm going to do is, because I want to use 2 of these, but they're going to have the same footprint. They're going to be the same part. So let me attach the footprint right now. So if I click on this, so this was a SOT23 footprint. So if I click on that and I go to footprints, I want to search for SOT23. It pops up this in the filter. Is that correct? SOT23. That looks correct to me. So 1, 2, 3. Looks like correct SOT23. Let's go with that. So, oops. Or not. So sometimes you have to go to SMD package. Yeah, so maybe we have to go here like that. Okay. Okay. So now that footprint is associated with the part. So now if we copy paste this part, the footprint will still be there. So let's take it, we'll copy it, we'll paste it, just like what we saw in kind of the SparkFun thing. We'll sort of copy that. Actually, this is not the way they did it in the SparkFun thing. In the SparkFun thing, these were, oh, the NMOSs were down, right? They were on the bottom side down here. Like that. And then the PMOSs, so let's go back to our SparkFun thing. The PMOSs were up here. And so let's find our PMOS. Let's go back to our parts library. We find our P channel, our high current P channel NMOS, 1.4 amps. That's getting close. Oops. Okay, it doesn't like me playing it, so I'm just going to copy it directly. All right, we'll go back to DigiKey. We'll look up that. So is this our part? 1.4 amp P channel. It looks correct. If we look at the data sheet for that, so what do we have? We have gate, source, drain. So this one's GSD. So it's going to be a P channel MOSFET. It should be GSD. So let's look for that. Oops. So hit A to add part. We'll do PMOS, see if we can find it there. So was it DSG? DSG, now I'm losing my mind. Nope, GSD. GSD, there we go. See, would you have known automatically to click on the fifth one? Nope, right? So you gotta be really careful. And there's no default footprint, so just like the other one, we'll add it later. GSD, okay. Now this thing, we'll rotate that like that. Okay, now let's go back to the SparkFun example. Now look at the way this is shown, right? So this has the VCC in, and it's a gate that blocks VCC in from passing to VCC in the board. But look at the orientation of this PMOS. The body diode is blocking current from left to right. If we go back to our thing though, look at this. The body diode is not blocking current from left to right. This is another huge mistake students make. They do transistors backwards. So these transistors have a body diode, which means they're not capable of blocking current in one direction. So we want to make sure that at the schematic level, we have this oriented properly. So in this case, what we would do is we would take this part, oops, hit escape to get out of part add. We'd take this part, well, we can mirror it if we want to, or we can right click it and do mirror horizontally. Yeah. So now, same part, but now it's shown with the proper source and drain. Now we might as well go attach that footprint to this. So the footprint for this should be the same. It should be this SOT23. And now we can copy that and paste it over here. Okay. Let's finish this off. And I don't like making the videos too long. I'm just going to finish this off and then we'll call this good for a video. So the 10Ks, you saw a lot of you with your schematic presentations, you were using some big old weird resistors. I'm going to show you how to get the proper resistors here. So again, I'm going to grab one resistor, associate the proper footprint for it, and then I'll copy paste that resistor as I do my design. So in this case, we have so we want to place, add symbol, or just click the A key. So if we do resistor, this is not always the best way to find it. So I always like RUS, but I I kind of actually prefer the small one. So a lot of the symbols you see in KiCad are a little bit too big. They show up a little bit too big. So I'm going to do R small US. What does US mean? US means it shows a resistor with a little wiggle. So European standard is usually to show resistors as a box, like a tube. I kind of like the wiggle, so we're going to do the wiggle. So, and for now, I'm gonna kind of place this off here because I plan on using this multiple times. I'm going to have a lot of resistors for this design. I'll just put it there. Hit escape to exit part thing. Let's go to this resistor. Let's associate it with a proper footprint. So the footprint, it should be SMD. So this should be resistor SMD. We're going to go down to 0603 metric, but let's do the hand solder. So the hand solder version is going to, or sorry, 0603 imperial, which is 1608 metric. The pads are going to be a little bigger to make it easier to hand solder for us. So I'm going to double click that. Now it's associated. So now this resistor is the symbol that I want, and it has automatically the associated footprint. So it makes it really easy for me to just copy paste this now. If I don't add the footprint now before I copy paste, I'm going to have to go back and add this footprint to every single stupid resistor in my design. So now we're just going to put one here-ish. And one here-ish. And now we'll wire this up. And I want to change the value of this from R small to 100K. R small to... And then we'll use the same terminology, so we'll call this... Sometimes if you already have a wire connection, it doesn't want to place a wire. So I double clicked it to stop, to actually place the wire. And now I'm going to place a label. I'm going to call this, I'll just use the same VCC in. And 3V3 in. We can place the symbol now. We can add the wire later if we want. So the nice thing is if you place the symbol before the wire, it lets you, hovering over that little pin makes it know. Okay, so now we got to put some grounds in here. So I like to just copy paste them like that. And then this one will be VCC and this one will be 3V3. So bad power. Okay. Now this isn't great. I mean, we can clean this up a little bit. So one thing we might want to do to clean this up is we might want to, we might want to at least, instead of having those names cut off by the, by the wire, let's move them over here to clean it up a little. We might want to move these over just so it's a little more clear. We just don't want the names overlapping. Okay, this looks pretty good. And if we wanted to, we could tighten this up. We don't need to leave quite so much space. Whoa. Okay, so that looks pretty good in terms of copying this. And we'll call it good for the video here, and we'll continue on with this in the next video. Thanks.